cardiovascular control center inside of the medulla. There's a cardiovascular control center and there's a respiratory control center, both of which are going to work in conjunction inside the medulla. That's your coordinating center for basically regulating heart rate, vessel constriction or dilation, as well as respiratory rate. The efferent pathways under this condition will result in slowing down of your heart rate and dilation of your blood vessels. The goal is to lower your pressure, right? You have high blood pressure, what are you going to do? You're going to dilate your blood vessels to try and reduce that resistance. Pressure down, you're going to slow down your heart rate so that it's not pumping so fast and forcing blood flow at a higher rate, which will also have an impact on your pressure. So for your mean or blood pressure, what we're really looking at is a decrease in heart rate and a decrease in resistance in the vasculature. With me so far? So, we have two different types of high pressure baroreceptors. We have one that is on we have one that is on your carotid sinus, and we have one that is part of your aortic arch. The carotid sinus are your baroreceptors that are going to communicate information about blood pressure that is going where? To your brain. Okay? That's going to be communicated by cranial nerve 9. For those of you that did 503, that's the glossopharyngeal nerve, which will show up on the next slide. So if you don't know how to spell it, it'll show up. The carotid sinus tells information about blood pressure of blood that is going to go up and feed the brain. On the aortic arch, this area here, these are your high pressure baroreceptors that are going to give information about the blood that is going to the rest of the body. That's going to be communicated by the vagus, cranial nerve 10. Okay? Both of these are going to work together to provide information to the medulla about the status of your blood pressure, whether it's going to the rest of the body or whether it's going to your brain. The most important thing to take note of is that these are going to work in concert with each other in order to make sure that your blood pressure doesn't go too high or too low. This shows the actual nerve that I just mentioned a second ago. So we have over here, you have your glossopharyngeal nerve, that's cranial nerve 9. The cell bodies for those are going to be in your petrosal inferior ganglion. That's where the cell bodies will reside for anything that's traveling through the glossopharyngeal nerve into and out of the medulla. So if we're looking at glossopharyngeal, cranial nerve 9, what information is communicated via this nerve? Blood pressure going where? Brain, okay? This is communicated through the sinus nerve from the carotid sinus. Those high pressure baroreceptors will use this pathway in order to send signals to the medulla. The other one will be down here, your vagus and your nodos. That is where the signals for the rest of your systemic circulation are going to come inside. Cranial nerve 10 is going to receive all of your stimulatory signals, or the glutamate that is going to be fired in through the cell bodies in the sensory nodos ganglion that will go into this area here on these regions of your medulla oblongata. So we're going to talk about these three parts, the nucleus tractus solitarius and the dorsal motor nucleus, as well as the nucleus ambiguus. Okay? You'll notice that cranial nerve 10, your vagus, is going to communicate with both the nucleus ambiguus and the dorsal motor nucleus of the vagus. They're going to have a role primarily in the control of the vasoconstrictor or vasodilator functions of this feedback system. Anybody have questions about the nerves that are involved before we go on to the next? Glossopharyngeal, cranial nerve 9, carotid sinus. Vagus is cranial nerve 10, aortic arch. Okay, so the reason I wanted to point that out is specifically because this is a figure that I gave you before. talk about these guys up here at the top. We've already discussed a little bit about the nucleus tractus solitarius, the dorsal motor, and the nucleus ambiguous. These are, maybe I should put them in the right colors. So purple is specifically looking at this guy. That's the purple circle there. Your green is the nucleus ambiguous. And the red for this figure is the nucleus tractus solitarius. So these three circles are going to be involved in this baroreceptor response. Okay, so starting down with any of your receptors that are going to be sending signals coming from the left side of the heart, right? Because this is looking specifically at high pressure systems. We haven't gotten to low pressure yet. That's going to come toward the end. So starting with your high pressure system, your aortic arch and your carotid sinus up here, they're going to communicate your sensory information of blood coming out of the left side either to the brain or to the rest of the body, and it's going to communicate it to these two regions up here. Specifically looking at the nucleus tractus solitarius. That is the first spot where these afferent signals are going to be received. From that point, there will be interneurons, which are in black, that will communicate with the other motor areas. In this case, we have two that we're going to look at. We have a cardioinhibitory area, and we have a vasomotor area. So the cardioinhibitory area is up on the right. That's your dorsal motor nucleus of the vagus, as well as your nucleus ambiguous. We're looking at purple and green. Those are cardioinhibitory areas. If it's cardioinhibitory, what do you think happens if you stimulate nerves in those areas? It slows down the heart rate. Okay? So in this case, if you stimulate because of a high mean arterial pressure, those baroreceptors in the carotid sinus or the aortic arch, are you going to want to excite or inhibit these two regions of the cardioinhibitory area? Say it louder. You said it right. Say it louder. Excite. You want to excite it, okay? Because you want to slow down your heart rate. Okay? So, what we have here is something that by default, if you trigger it, it's going to slow down the heart rate. The only way that you're going to increase your heart rate is if you inhibit this cardioinhibitory area. But by default, any excitatory signal that goes there is going to slow down the heart rate and cause bradycardia. Okay? With me so far?
So, I heard that if somebody's in abnormal heart rhythm, if you bang on their chest really hard, that it will stop their heart for a moment and then it will pick up okay. Is that hitting this mechanism?
So,
portal thump, I think is.
Yeah, so, well, if you hit, has anybody else have any experience with this? Anybody who works as an EMT? Do you want to explain what's going on here?
Well, it wasn't an EMT, but I got hit really hard with a baseball, and
What happened?
well, my heart kind of stopped for a second, and I fell to the floor, like I felt like I was fainting, and then I picked up a little bit later.
So what do you think if you actually hit the heart itself or that area? Which one of these would you likely trigger? The aortic arch, right? Sorry. Because that would be right there, coming right out on the left side of your heart.
Yeah, it hit me like right in the center of the chest.
So you're right. What you're doing is it's not just that though. You also have ways to be able to stimulate the vagus. Most likely, what this is actually doing is that would be one of the reflexes that you could have. But if you actually hit the vagus and you stimulate the vagus, you can also do that with the Valsalva maneuver, which is basically holding your nose and trying to pop your ears. That's a way to stimulate the vagus as well, and that can slow down your heart rate. But if you hit it hard enough, it can cause it to sort of stop until it gets that signal again. Question? Okay, so cardioinhibitory area we've already covered. Going back to our vasomotor area, this is one that we haven't started talking about yet. But the vasomotor area specifically will stimulate vasoconstriction. Okay, so if you want to dilate your blood vessels, what do you want to do here? Do you want to stimulate or inhibit? You want to inhibit this. Okay, so that's actually what's happening up here. It's a okay. So right here, I can stop. There we go. Okay, so right in here, you see the two green boxes that have little plus signs in the middle? Those are the excitatory signals that are coming from the nucleus tractus solitarius into those two cardioinhibitory areas. That's your excitatory signal to slow down your heart rate. The little red box that has a negative signal, that's a negative signal that you're sending to that vasomotor area because it's an inhibitory interneuron. So when you trigger the carotid sinus of the aortic arch, you get afferent sensory signals that are going to be sent into the nucleus tractus solitarius, and then it's going to branch out in different interneurons, which are sort of the middleman to communicate between the signal coming from the body, the afferent side, and the signal going to the body, the efferent side, so the motor signal. You get excitatory signals that are going to go to your cardioinhibitory area, so the net result is that you're going to slow down the heart rate. And you have an inhibitory signal by the C1 nerves. Those C1 nerves normally will cause vasoconstriction. So you want to inhibit those C1 neurons in order to promote vasodilation. All of these are going to work together to slow down or lower that blood pressure. Because the triggering response is because you have a higher mean arterial pressure. So this is your feedback mechanism in order to get your blood vessels to dilate, your heart rate to slow down, in an attempt to bring your blood pressure back in. How do we feel so far? Okay. All right, so the end result, mean arterial pressure, elevated. Feedback signals will tell you to try and bring that back down. High pressure baroreceptors are specifically going to respond to elevated blood pressure by trying to lower the actual blood pressure. Your low pressure baroreceptors do it in a different way. Okay, so this was just to highlight those C1 nerves right here that are going to be responsible for normally causing vasoconstriction, that you want to inhibit those in order to promote vasodilation. Okay. Now, just because this is a feedback center that goes to the brainstem doesn't mean that you can't have any information coming from higher levels of the brain. The hypothalamus can integrate information coming from the cortical regions, and it can collect information in order to augment the cardiovascular control center. Okay? It's the reason why you've, I don't know how likely any of you have ever experienced this, but anybody who's watched Gone with the Wind, you get the vapors, you get too emotional and then you pass out. Okay? It's a drop in blood pressure, and it's because of an emotion from the cortical region that gets sent to the hypothalamus, which gets sent to the medulla and triggers a drop in blood pressure. Okay? So very strong emotion can be used to precipitate a drop in blood pressure with syncope. Syncope is just the word for fainting. You also can train animals to elevate or drop their blood pressure through reward reinforcement, basically taking advantage of this neuronal communication. So there's an automatic feedback, but there is also input from the higher centers of the brain. All right, now, the next thing I want to talk about is specifically looking at another type of receptor. We have different types of chemoreceptors. Okay, we have different types of chemoreceptors. There are central chemoreceptors and peripheral chemoreceptors. We'll get into these a little bit more so specifically when we get into respiratory. We have to introduce them now because since your medulla has a respiratory control center and a cardiovascular control center, they are integrated. So you're not quite free of all respiratory stuff before we get into it, and once we get into respiratory, you will not be completely free of all cardiovascular. So this is one of the places where they're going to tie in. One of the things that happens is your peripheral chemoreceptors are going to be able to measure a change in cardiac output. if your cardiac output happens to go down, okay, one of the things that can happen if it's a severe enough drop in cardiac output is it will result in an inability to meet the demands of metabolically active tissues. These are not actually looking at cardiac output per se. It's specifically looking at the metabolic consequences of reduced cardiac output. So you don't have enough time or you don't have enough perfusion to get gas exchange. You will get an accumulation of CO2 in your tissues and you'll have a drop in the partial pressure of O2. That will be something that will be very important to pay attention to, specifically when we get into the respiratory unit for how hemoglobin is able to carry oxygen. But if you have a drop in overall cardiac output, that elevated peak CO2 will cause a more acidic condition. This is normal. Metabolism on a cellular level is going to produce organic acids as a byproduct of metabolism. So it's also going to produce your CO2, both of which will conspire to drop the pH. If you don't have adequate perfusion, you won't have adequate gas exchange, and you won't be able to remove those acids. That's going to be sensed by your peripheral chemoreceptors. Okay? They'll be able to sense that drop in PO2. They haven't installed the software for my little device on the desktop yet, so I can bring my laptop. Okay. So when you trigger those peripheral chemoreceptors because you have a drop in PO2, that signal is going to be sent up to the cardiovascular center, coordinating center, and the respiratory center. They are in close proximity, so a signal to one is also going to usually send a signal to the other. So we will have an effect on respiration, but we also have effect on heart rate. In that coordinating center, what do you notice about the effect on the efferent side of changes in blood gas levels? Is it the same as what we saw with the baroreceptor? No, what's different? The vessels. It causes vasoconstriction instead of vasodilation. Why would you want to cause vasoconstriction? Well, so if you're causing constriction, you're going to make the vessels a little bit narrower. What are you going to do to blood flow? Well, if you're looking at resistance vessels, so you're going to pass through, drop the pressure a little bit further. You're going to be moving a little bit slower by the time you get to the capillaries. Okay? So, because as you increase that resistance, you're dropping that blood pressure. It's the balance between the two that will have an overall flow change to decrease it. The slower the flow, the more time you have for passage. Okay? So, heart rate is going to slow down from this mechanism, and your blood vessels are going to constrict. So, it's a little different than what we saw before. So in this case, what's another term for low partial pressure of CO2, or sorry, low partial pressure of oxygen in tissues? Hypoxia. It's different than hypoxemia, which is low partial pressure of oxygen in the blood. Okay? But if you're talking about the tissues, which is what we're sensing here, because it's going to communicate directly with the blood, we are going to get vasoconstriction and bradycardia. We're going to slow down the heart rate. That's different than what we saw here, right? So we have vasodilation if the problem is sensed by your baroreceptors. We had vasoconstriction if it's a problem sensed by your peripheral chemoreceptors. Yeah?
Are the chemoreceptors responding to the gas changes or the pH changes or both?
Both. Your peripheral chemoreceptors are specifically looking at gas. Your central chemoreceptors are located in the medulla. They actually sense elevations in or changes in partial pressure of carbon dioxide by way of sensing pH changes in the cerebrospinal fluid. But for your peripheral chemoreceptors, they will actually sense lower partial pressure of oxygen circulating in the blood. So they sense the gas itself, mainly oxygen, and to a lesser degree, your CO2.
Thank you.
We get into that when we cover. somebody's hypoxic, does their heart rate slow down? Doesn't. So if the feedback mechanism says that if you have low PO2, the signal is to cause vasoconstriction and bradycardia, how come we actually see tachycardia in real life? So, your sympathetic system will kick into play if you are stressed out. And that can have a feedback mechanism. But specifically just looking at any degree of hypoxia that is typically only going to show up when you have severe hypoxia, what actually is occurring is you are not only sending information to the cardiovascular areas of the medulla, you're also sending information to the respiratory areas. So what's happening at the same time is that you're getting that signal going from this low metabolic issue, triggering your peripheral and your central chemoreceptors. The difference is that both of them are also going to trigger an increase in ventilation as a way to compensate for this blood gas imbalance. All right, so your normal feedback sent by those peripheral chemoreceptors will slow down your heart rate. But you also get a concomitant signal going to the respiratory centers of the medulla to start to increase ventilation. So you're going to start breathing faster if you're in their hypoxic condition. That faster breathing causes two effects, which are shown up here. Stretching of the lungs. The canoreceptors in the lungs will actually send afferent signals to that cardio-inhibitory area to inhibit it. So if you're going to inhibit an inhibitory signal, you get a reflexive increase in heart rate to cause tachycardia. The other thing that happens as a consequence of increasing ventilation is you're blowing off more of that carbon dioxide. So the amount of oxygen in your partial pressure in the blood, and therefore in the cerebrospinal fluid, is going to go up. Your PCO2 is going to go down. High levels of PCO2 means acidic pH. If you have a low PCO2, that means a more alkaline or basic pH. So elevated ventilation causes the PCO2 to go down, which means your pH is going up. Your central chemoreceptors are going to help to promote an increase in ventilation. When that PCO2 drops, it sends that inhibitory signal to the heart, the cardio-inhibitory part of the disease. So two signals, drop in PCO2 and the stretching of the lungs because you've elevated ventilation are both going to send a competing signal to the same cardio-inhibitory areas of the body. So you're going to get a stimulatory signal coming from peripheral chemoreceptors to slow down your heart rate. You're going to get two inhibitory signals because of an increase in ventilation to that same location. So basically, which one's going to win out? It turns out that your negative signals are going to win out and you have a reflexive increase in heart rate. So the physiological response to hypoxia is tachycardia, despite the fact that peripheral chemoreceptors communicating with your cardiovascular coordinating center in the medulla directly contributes to bradycardia, but it's overridden by the fact that you also have an increase in ventilation sending an opposite opposing signal. If you didn't have an increase in ventilation, it would slow down the heart rate.
So if you felt a little out of breath, but you held your breath intentionally, it would override this a little bit.
So, yeah,
If
so.
you're at altitude or something.
Yeah, so if you, there's a little bit of a difference with altitude, which we also will talk about in respiratory. With altitude, the problem is that you could be breathing the same breathing rate, but the actual amount of oxygen that's available to you drops. And so that's going to trigger your peripheral chemoreceptors, not your central ones. But both of them will result in an increase in ventilation. If you were to hold your breath, you're right, it would cause, and it would exacerbate this elevation of your PCO2 value, which would slow your heart rate down because you don't have the lung stretch and that resultant drop in CO2 because you're intentionally building it back up. Yes?
So the lung stretch is going to cause mechanoreceptors to send an inhibitory response to the medulla
Yeah,
to cause an increase in heart rate.
yes, yeah. That inhibitory, the stretching of those stimulates mechanoreceptors, that afferent signal sends an inhibitory interneuron to that cardioinhibitory area.
I'm a little confused about like an example of when this is happening because at first you start talking about when you hold your breath, your heart rate goes up, but you're not ventilating at that point because you're holding your breath.
No, I said that if you're holding your breath, the high PCO2, the reflexive response is what measured by the peripheral receptors. If you were to hold your breath and have an elevated PCO2, your peripheral receptors are going to send that normal signal to slow down your heart rate and cause vasoconstriction. The first one we saw. That's the direct response of your peripheral chemoreceptors in the absence of any kind of competing signal. The increase in ventilation is your competing signal. It overrides that normal reflexive signal that would come into play. And so part of that is because you're stretching the lungs. The other part is when you hyperventilate, you're blowing off more of that CO2 so that PCO2 actually goes down. And because of that, it causes an increase in your overall heart rate. Yeah.
Oh, so since this is a competing system here, if you didn't have the peripheral chemoreceptor response, would the central response have an exaggerated increase in heart rate?
So, that depends on how severe, I guess, your hypoxia is and how severe your PCO2 is because it's specifically measuring it in the medulla. So it's measuring the change in pH that is showing up in your cerebrospinal fluid. So, yeah, measuring through the chemoreceptors, it's not measuring anything about PO2. So this actually doesn't come into play when you go to like high altitude. This would be more, you have inadequate ventilation, but you are still metabolizing and producing a lot of CO2. So not because you're not having access to enough oxygen, you're just not breathing at that same rate. So your central chemoreceptors will stimulate a hyperventilation that will cause your heart rate to go up until it balances out. Because as soon as you start to get that PCO2 to go back down, everything is gonna basically reverse. Your central chemoreceptors are constantly in flux, and so are your peripheral, but they don't play as much of a role in the elevated levels of PCO2. Yeah.
So is hyperventilation kind of a runaway condition because your CO2 levels are dropping kind of uncontrollably and your lung stretch, and so your heart rate just keeps...
Well, it'll go up, right? But what happens when your heart rate goes up? If your PCO2 is dropped, you're going to stop sending that signal to the central chemoreceptors in the peripheral. They're only firing in response to elevated CO2. If the CO2 starts to drop, then they're going to stop sending that signal, and your elevated heart rate signal will start to slow back down again. Once you get back down into your normal physiological range. So these are negative feedback cycles. All right, how are we doing? Pretty good? This is going to be the content that will be covered in the review session. So if it seems like a lot, there is that review session this afternoon at 5 o'clock that will help to go through this. Oh, one other announcement that I realized, somebody told me in office hours that you might not have realized that you can connect with the other members of your team if you didn't already see that in Top Hat. There's a discussion board that each of you will have access to, one discussion board. And if you go in there, you can see everybody else that's in your team. You can communicate with them if you decide you want to study as a group before the TBL next week. You have a way to contact the other members of your group. And it's your discussion board is only assigned to the other members of your team. Okay, so if you're in team 12, it'll say discussion board 12. Okay, and then you can communicate with the other members. It'll have a list of who's in your group. I realized that I had forgotten to make that announcement when I assigned it, and I learned yesterday that I guess it's kind of hidden, not as obvious in Clubhouse. So I wanted to let you know that if you haven't already contacted your teammates, you can do that if you decide to do that. All right, so that's our high pressure system. Now we're gonna get into our low pressure system. Where do you think your low pressure signals are going to come from? Your venous system. So if your systemic venous system. So if we're looking specifically at your receptors, right there in your right atrium, okay? You have two different types. You have type A fibers and you have type B fibers. And the biggest difference is how they fire. What is it that they are monitoring? What are they firing in response to? But they're located in your right atrium. So they're going to measure blood pressure from the low pressure side of your circulatory system. All right, so this is coming back from systemic circulation through the venous return to the heart on the right side and getting ready to head into pulmonary circulation. All right, so high pressure is going to measure blood coming out of the left ventricle. Your low pressure is measuring the blood pressure that is coming back into the right atrium. In orange, you have your A fiber. This A fiber specifically, when is it firing? Related to the ECG, when do you see it firing? Right around atrial depolarization and therefore atrial contraction. So if it fires at every atrial systole, what are you measuring? What is this going to tell you information about? The way that your A fibers are firing. What does that tell you? Every time the atrial contracts, so heart rate. Your A fibers are going to give you information about heart rate. They're going to fire every time you have atrial systole. So it provides information about overall heart rate. If they fire more frequently, it's because the heart is contracting more frequently. So your heart rate is up. If they fire less frequently, your heart rate is down. So A fibers specifically will give you information about heart rate. Your B fibers, on the other hand, what do you notice about the way the B fibers are going to respond? First of all, is it uniform?
No.
No, it's not. What do you notice about the frequency?
Jesus.
The frequency is increasing, right? So if the frequency is increasing, and what is the timing of it? So it actually starts, where does it start? The very first one. It starts right there at ventricular contraction, right? So during the contraction and relaxation of the ventricles, that's when your B fibers are. The difference between your A and B is the A is pretty much a uniform frequency during atrial systole. For ventricular systole, your B fibers start off comparatively slow, and they speed up in terms of the firing frequency of those B fibers. What's happening in the right atrium during this part of the ECG? Atrial fibrillation. The narrowing space of the frequency of the firing? Yes, it's getting more narrow, so they're firing more rapidly. Each of those vertical lines is representing an impulse being fired by that B fiber. And because they're getting closer together, you can think of the x-axis as time. They're firing impulses more frequently. So if you're getting a stronger firing rate or a faster firing rate as you progress through ventricular systole. So when you start ventricular systole, what is closed? What valve is closed? Valve or valve? At the beginning of ventricular systole. Both of them are closed, right? So both your atrioventricular and your semilunar valves are going to be closed because you have that isovolumetric contraction. But the important part here is that your atrioventricular valve is closed. Okay, so you've already lost all of the blood from the atrium after atrial systole, so your A fibers are done. Atrial systole is done, you close that atrioventricular valve, and now your B fibers are starting to fire. So that's the transition between the P and the QRS. That's the transition between your A fibers firing, because that's the end of atrial systole after when you begin that QRS depolarization, and the beginning of the B fiber signaling after you close that AV valve and your ventricles are now starting their systolic contraction.
So that part is not depicted in B fibers. So you have atrial, atrial systole, and then you have the ventricular depolarization, but that space is not represented in those things.
Yeah, because that's the repolarization of the atrium. So when your atrium, you don't see the T wave of your atrial repolarization. You don't see that showing up because it's obscured by the QRS. Your A fibers are only firing during systole. So when your atria start to relax, there's that slight little, I guess you could think of it as like a momentary gap, but they should line up pretty close. It's so small. This is just a diagram to show that it doesn't happen at the same time. They don't fire at the same time. A finishes firing and then B starts. Because B starts when ventricular systole occurs. A is only during A. Because it's a timing thing, they fire in sequential order. But the important part to note about the B fibers increasing in their frequency is what is happening. Somebody had said it before. What is happening during that ventricular systole? What's happening to the atrium? It's filling, okay? So if you are seeing an increase in the frequency of these B fibers filling, during that filling, what is this measuring? Venous return. It's measuring volume, okay? The more full your atrium gets, the more rapidly those B fibers are going to send signals. All right? So your low pressure baroreceptor, A tells you information about heart rate. B tells you information about venous return. It's measuring your central venous pressure as blood is returning and filling the atrium. Okay? This is going to come into play specifically when we start talking about your baroreceptor versus something reflex versus something called the Bainbridge reflex. It's two different ways to respond to blood pressure increases. Okay, so baroreceptor directly measures mean arterial pressure, systemic arterial pressure. This is measuring the central venous pressure on the low pressure side, specifically in reference to volume. Pressure can be because of constriction of blood vessels increase, or it can be because you have more volume in a set radius. All right. So our high pressure and our low pressure, two different sets of responses. Your high pressure baroreceptors are, what are the two? Oh, sorry, go ahead.
I'm sorry, Lucy. I have a question about the physiological placement of those receptors. So if they're located in the superior and inferior vena cava of the B fibers, is it nerve endings that are polarizing the regions where they can get that feedback?
Yeah, so when we're talking about these receptors, they're always going to be nerve fibers. Basically, they are mechanically gated. So if you have an increase in pressure, you're putting more force, mechanical force on the nerve endings of these. You're compressing them, opening channels, which causes them to start firing. The more pressure, the more of those mechanically gated channels open, the more frequently that nerve is going to fire. So that's what's happening here. That's why it fires faster. As you get more and more full in the atrium, there's more and more pressure on these B fibers, which causes them to send the electronic signal a little bit more fast. Okay, so looking at our high pressure and low pressure. Your high pressure, we have two different types of high pressure baroreceptors, which are located where? Carotid sinus and aortic arch. Your peripheral chemoreceptors are also located there too. You have aortic bodies and carotid bodies located in the same general area. So you get your high pressure baroreceptors and your peripheral chemoreceptors are sensing the same blood as it passes. Your low pressure baroreceptors are going to be your A fibers and your B fibers, and they are going to be located where? In your right atrium. Okay, so it's going to measure coming back from the systemic circulation. The difference in the response is that if you were to trigger, because of an elevation in blood pressure, those high pressure baroreceptors, you get a lowering of your heart rate and basically mass vasodilation across the board. For your low pressure baroreceptors, you get an increase in heart rate from this feedback signal. And you get vasodilation specifically to the kidneys. Why? What are they both controlling? They're both going to control what? What parameter? They're both trying to control blood pressure, right? High pressure baroreceptors are going to control it directly by causing dilation, by slowing down the heart rate. Your low pressure ones are going to try to control blood pressure by controlling blood volume. So if you have an increase in blood volume, and that's the cause of your increase in blood pressure, how are you going to get rid of that excess volume? You're going to excrete it through the kidneys. Okay? So, low pressure baroreceptors will elevate heart rate to increase perfusion of blood going to the kidneys by specifically targeting vasodilation of blood vessels feeding the kidneys. What that does is it increases renal blood flow, which means that your filtration of fluid is going to go up. You'll increase the overall rate of fluid excretion by increasing renal blood flow to the kidneys. Now we'll get to that when we actually get to the renal unit, about how that all works. But at this point, what you need to understand is that the low pressure baroreceptors are controlling blood pressure by controlling blood volume. That's why they have a different response. Okay? High pressure baroreceptors from the left arterial side will give you a direct control of your blood pressure by affecting vasodilation and affecting your overall heart rate. The low pressure ones are going to do it by controlling blood volume. They're going to try to eliminate fluid. Okay? Do that. Dilate the vessels so that you can divert a higher degree of your blood to the kidneys to increase the amount of fluid that can be excreted from the body. If you reduce the volume of blood, you'll reduce the overall pressure. Your Bainbridge. So your baroreceptor reflex is the first one we talked about that will cause a decrease in heart rate. Your Bainbridge reflex causes tachycardia, increased heart rate in response to an increase in your venous return. It's sensed by those low pressure B fibers. It can saturate, but excuse me. The intent is to elevate your overall cardiac output in order to promote an increase in renal blood flow to eliminate that excess fluid. So you have two competing signals, depending on whether or not you are under conditions of excess volume or depleted volume. So let's say that you took a second and you did an intravenous infusion. So you started and you did an experiment where you did an intravenous infusion into the body. So you put in a certain amount of fluid. You are specifically increasing the overall fluid in the blood, all right? your right atrial pressure is going to increase, okay? That's gonna increase. What's gonna happen? You're gonna have an increase in cardiac output because you have more venous return. What happens when you stretch the ventricles? You're going to initiate that Frank-Starling mechanism to increase your stroke volume. You're gonna increase your overall cardiac output as best you can. Now, the Bainbridge reflex doesn't have as much of an effect on stroke volume as it does on heart rate, but this specifically is just looking at heart rate. So if you were to increase your cardiac output, one of the things that happens is you're going to increase the arterial pressure on the left side. That will trigger your baroreceptor reflex, which has an inhibitory effect or a slowing down effect on your heart rate. Okay, so that's the first one we talked about. The high pressure baroreceptors will slow down heart rate because your mean arterial pressure has become elevated. Your mean arterial pressure is elevated because your cardiac output went up because you increase the volume and you increase the pressure by the fact that you've added a liter or two of solution to blood. The other thing that happens when you increase your right atrial pressure is you're also going to stimulate those atrial receptors. Those receptors trigger that Bainbridge reflex that I mentioned that will cause an increase in your heart rate. So you have two different mechanisms. You have a decrease in heart rate being triggered by baroreceptors, and you have an increase in heart rate being triggered by the Bainbridge reflex. Which one is going to prevail depends on what the fluid status or the volume status is of the body. One other thing that I didn't mention yet that will help in the response to excess amounts of fluid is atrial natriuretic peptide, ANP. We'll talk about this again when we get to renal, but one of the things that happens in response to that increased venous return because of volume is these atrial myocytes will also be releasing ANP, in addition to dilating the blood vessels filling. All right, so two different signals that are both going to control heart rate, and they're both going to respond to pressure. They're just going to do it at different parts of the body, and they're going to have a different effect. How do we know which one is going to prevail? This is the one that I gave you guys ahead of time, specifically because it's a little convoluted, and it might be a little hard to understand that biphasic effect that you see with heart rate. On the left-hand side, you have volume depletion. So let's first start and look at, down here you have your effective circulating volume. So 0 is sort of your starting point, your baseline. At that baseline, anything to the left means that you are depleting volume of the blood. Anything to the right is volume loading. So you have more volume than at your normal starting point. The y-axis just shows the percent change, that it's below normal or above normal. When you're under this blue half here, that volume depletion, both of these are going to work in concert to try and increase the overall cardiac output. Okay? Cardiac output, because it's the relationship between heart rate and stroke volume, is going to have to take into account your overall heart rate and your overall stroke volume to generate a cardiac output for the heart. Your baroreceptor reflex is what is prevailing on this left side. All right? So the high stretch, if you were looking at a slowing down of heart rate, that's what's happening from left to right. As you increase your circulating volume, but you're still technically in that volume depleted region, you're elevating that blue line on the bottom, which is your stroke volume, but you're slowing down your heart rate to make your cardiac output increase. That's your baroreceptor reflex. The baroreceptor reflex is that effect on heart rate that will increase as you continue to lose more fluid. Because as you lose fluid, what happens to your blood pressure? Okay, so if you're in a volume depleted, like a hemorrhagic state where you've lost a lot of blood volume, if your blood pressure is relatively low, if you started to do an infusion to bring you back up to normal, your heart rate would be very high. It would gradually start to slow down as you started to build up more volume. Okay, so you do have that relationship. In a volume depleting position, you will actually elevate heart rate. If you have a volume loading condition, you will also elevate heart rate. And the reason for that is that one of the things that you can't do is you can't really continue to increase overall stroke volume. You maxed out stroke volume. That's your Frank-Starling mechanism. You can only increase that up to a certain degree, and at that point, you're going to basically be at your most efficient. That's the biggest stroke volume that you can have, and it's eventually going to plateau. That happens when the Bainbridge reflex kind of kicks into place, and that's what's showing up here. This Bainbridge reflex, on the right-hand side, shows that you have that tachycardia being signaled in response to excess amounts of fluid. Because again, fluid is continuing to increase as you move along this green half of that figure, right? Because your stroke volume has kind of maxed out, the only way you can increase cardiac output is to elevate your heart rate. So under volume depleting, you have two opportunities, right? You can increase your stroke volume and you can alter your heart rate. Once your heart is already working at its max to be able to get that stroke volume at its peak, you can't elevate your cardiac output anymore by changing stroke volume. So for the Bainbridge reflex, it's really only affecting heart rate. It has a very modest effect on stroke volume. Stroke volume at this point, when you are at your normal operating level, and then any time that you do an infusion, you have a maximum stroke volume that your heart can achieve, based on size. It's surrounded by connective tissue in the pericardium, so it can't expand beyond that cavity. All right, so there is a maximum amount. How do you get this increase in stroke volume on the depleted side? What's that mechanism? Intrinsic mechanism to increase stroke volume based on venous return increase. Frank-Starling, right? Frank-Starling, right? You stretch it, you basically make every sarcomere is able to be more efficient in its contractile force, so you can have an intrinsic increase on this bottom depleted area. So we're looking specifically at here. This increase is in the blue line there. That's your Frank-Starling mechanism. So that increase in stroke volume is going to happen at the same time as this decrease in heart rate. But the two of them together cause a net increase in your overall cardiac output, because cardiac output, by definition here, is your heart rate times your stroke volume. That's effectively going to go away when you get onto a volume loading side. So if you have an elevated blood volume, and that's what's causing your increase in blood pressure, kidney vessels are going to be dilated, and you're going to end up with basically maximum stroke volume that your heart can do. And the only way that you can increase cardiac output in order to try and eliminate that fluid is by elevating the heart rate. So two different types of conditions. Volume depletion of your blood, lower than normal, your baroreceptor signal is going to predominate. On a volume loading above what is normal, you're going to see more of the Bainbridge reflex responding, because the Bainbridge kicks in when you need to eliminate fluid. The baroreceptor kicks in when you are either at normal or lower. Okay, so they are competing, but they basically win out over the other one based on the fluid volume level of the blood. Anybody feel a little better after seeing this and walking through it?
So the baroreceptor is causing a decrease in heart rate.
Yes, moving from left to right.
Okay.
So when we're specifically moving from left to right, we're starting here on the left side. If you just move straight across from left to right, your baroreceptor response causes bradycardia. Your Bainbridge, as you continue to move from left to right in volume, is going to cause tachycardia, right? But if you were moving and slowly, like let's say you were bleeding consistently, hopefully that never happens, but in theory, if you were consistently losing volume, the baroreceptor would actually result in an increase in heart rate as the volume dropped to the point where you couldn't maintain that stroke volume. So that's why you can affect stroke volume when you are less than your optimal blood volume, because you don't have as much blood coming back in venous return, so your stroke volume will be a little less, right? So as you start to lose fluid, you can increase your heart rate in order to compensate for the fact that your stroke volume is gone. As you gain fluid, the only thing that you can really alter is your heart rate, because you're already at that point where your heart is maximally filled at every single beat.
So in hypertension, is the vein surgery what's causing?
It depends on what's causing hypertension. So if hypertension is due to an excessive amount of fluid, then yes, your vein bridge is the one that's going to come into play. If it's caused because you have excessive stimulation of your sympathetic system that causes restriction of your blood vessels, that will elevate blood pressure. That doesn't actually have anything to do with your overall volume. So it depends on what your volume status is. All right, got about 15 more minutes. We're doing pretty well. How do we feel? We don't have that much more to go through. Okay. We're going to move on. All right. This is just an overall summary. I like summary figures. You're going to see this come into play, especially when we get to renal. There are some really great, nice big summary figures and all the complex stuff that we're going to talk about. I put them in there so that when you're going back through them, sometimes any of the figures that I find that are in lectures are usually going to come from one of the books that are on reserve in the library, and that's intentional so that as you're studying, you can go to the source where that information was, so you can read up extra information based on the figure we talked about. But that doesn't mean that there aren't other resources out there that have figures that might be a little better or even a little clearer sometimes. So I'll include those occasionally just to give you simplified summary ones. In this case, this is specifically looking at your sympathetic and parasympathetic. The SA node is what's really going to be altered by your parasympathetic. Your ventricular myocardium doesn't have any real effect from the parasympathetic side. It's not affected by any parasympathetic firing. Parasympathetic nerves will typically only innervate the SA node in order to control and regulate the overall heart rate. The sympathetic nerves can innervate not just the ventricular muscle, but also your SA node in order to control not just heart rate, but then stroke volume for increasing the contractility of those ventricular myocytes. That goes into, do you remember I want to say it was lecture 2, that Barnum-Levy figure where we talked about the beta adrenergic receptors and how they would respond to catecholamines. They would also respond to norepinephrine in your ventricular muscle, right? Elevate cyclic AMP, activate PKA, phosphorylates what? Phospholamband to increase repolarization, troponin I to remove that inhibition so you can get contraction occurring, and the L-type calcium channel to promote more calcium coming in by opening these channels. Okay, so you don't have that coming from the parasympathetic side, but you can elevate the stroke volume and the contractility by stimulating the sympathetic system. So sympathetic can trigger not just an increase in heart rate, but it can also increase your stroke volume. Parasympathetic's effect on the heart is really just heart rate, okay? But as you know, your stroke volume and your heart rate together are going to tell you information about your cardiac output. Okay, so that's the same figure that we had talked about before, but now I want to talk about the difference between the cardiac output that we talked about so far, heart rate times stroke volume. That tells you how much, what's the cardiac output of the heart in total. How much blood your ventricle is pumping per minute. Typically around 5 liters per minute, okay? Can go up to 15 or 20 when you're under exercise or stress, but that just tells you what your ventricle is pumping. That doesn't tell you what your effective cardiac output is, which means that that's the cardiac output that's going into your circulatory system. If you had some kind of valve problem with the mitral valve, you're looking at the left side, let's say it doesn't close completely. It doesn't prolapse, which means that when the ventricle contracts, where's blood going to go? Back up into the atrium, so you can get mitral regurgitation, which means that even if your heart is pumping 5 liters per minute, maybe only 4.5 liters are actually going into the circulation, and per minute, half a liter is going back up and being regurgitated. Okay, so these are two different calculations that give you information about the cardiac output based on how much blood per beat and how many beats per minute. That just tells you what the heart's pumping. This will tell you how much of that's getting into your circulation. So this is your effective cardiac output. And it can be measured by the Fick principle. This is something that we did, we'll do this again when we get into respiratory, specifically when we want to measure information about gas exchange. But Fick principle is saying if you are looking at the value of a particular compound, a particular molecule, and how it changes in the blood between point A and point B, you can measure that based on how much is added or subtracted. So the easiest thing for us to do to measure effective cardiac output will be to take the information that you have about gas, oxygen levels, and relate that to what's happening after you've added more in. So the easiest way to kind of run through this is looking specifically up here at the top. You have a certain amount of blood in the pulmonary artery, right? Coming from the right heart, deoxygenated, so you're at your sort of low oxygen level. Typically around 15 mils of oxygen per deciliter of blood. That would be your concentration that you would find going into the lungs. On average, you would measure oxygen consumption, how much oxygen you're taking in per unit time. In this case, it on average would be about 250 mils of oxygen per minute. Okay? If you have 250 mils of oxygen per minute, and then you measure the concentration of oxygen in the blood on the pulmonary vein after you've added that rate, you typically will come up with about 20 mils of oxygen per deciliter of blood. So how can you figure out the cardiac output? You can look at the amount that you're adding and divide it by the difference between the before point and the after point. So in this case, we have 250 mils of oxygen per minute. It's also important to pay attention to the units that you have. So for this case, make sure I don't fall asleep on the time. You're looking here at your 250 mils of oxygen. So milliliters of oxygen is what we're measuring on all of these. We're looking at these mils per deciliter of blood, and we're looking at the time rate as being minutes. So if you want to use the Fick principle to figure out your effective cardiac output, you would take how much you're actually adding or subtracting, they should be roughly equivalent, to the system. In this case, it's 250 mils of oxygen per minute, and you would divide it by the difference between these two. So 20 minus 15. What's 250 divided by 5? 50, right? But it's 50 deciliters of blood per minute, which means how many liters? 5. Okay? So in this case, all of the blood that's coming out of the heart is going into the circulation. How are we going to collect these concentrations of blood gas levels in the pulmonary artery or the pulmonary vein? Where would we have to collect pulmonary artery blood to figure out the concentration? Where does it come from? What part of the heart? The right side, right? You could do a catheter into the right side of your heart, into the right atrium, the right ventricle, or the pulmonary artery itself. Why can't you just take venous blood?
Because there might be an issue with the right ventricle.
No, there actually might be an issue with not getting, you want to get the blood after it's passed through every potential capillary bed, right? So if you collect venous circulation somewhere in the body and there happens to be another capillary bed, you're collecting it not at the source where you have all the blood coming into the heart. You really need to make sure that you have already passed through every capillary bed, and this is the blood that is actually going to go to the lungs. So in order to get the QA value from this figure, you really need to do a catheter into the right atrium, the right ventricle, or the pulmonary artery, because that will give you information about what is the oxygen concentration in the blood that enters the lungs. You can measure your oxygen consumption, get your value, in this case it's 250, where will you measure your pulmonary vein? You can measure it from the pulmonary vein, but places that are easier to get to, any systemic artery. Why can you measure it at any systemic artery? There's no gas exchange between that pulmonary vein and any systemic artery. You haven't hit any of your capillary beds. You haven't had any chances for gas exchange. Once you have gas exchange to load up your blood with oxygen in the capillary bed in the lungs, it'll go through the pulmonary vein, through the left side of the heart, through the aorta, through your major systemic arteries. Before it actually gets to any of your capillary beds, it should have the same oxygen concentration. Okay, so you can measure from your systemic arteries, you can collect your pulmonary vein value. The goal is to get information about what is the concentration of oxygen going into the lungs, what is the concentration in the blood coming out of the lungs, and then what is the amount that you are adding into the system. That tells you your effective cardiac output because it should be equivalent to what we're seeing on the tissue side. You are going to have oxygen consumption that is in direct relation to tissue usage. Because if you don't, if you have a need for more tissue use for oxygen to get to the tissues, then you're going to elevate your oxygen consumption. Those feedback mechanisms are going to come into play that if you have an oxygen use in the tissues of 275, you're going to have a stimulation that will increase ventilation to get your oxygen consumption to 275. So you could do this in order to say information from the systemic arterial circulation. So you have oxygen, how much of it is leaving the system, and how much of it remains after you're done. That's the same thing, 250 divided by QB minus QA. And that will give you your effective cardiac output. That's different than your regular cardiac output under conditions of pathologies that mean that you don't have all of your blood leaving the heart. If you have some kind of regurgitation system because of a valvular defect, that's where you would have a difference in cardiac output equaling heart rate times stroke volume, and you would get a different result if you calculated it by the thickness. This is the easiest one to do because we're constantly breathing. We're always going to introduce more oxygen, so it's the easiest thing to measure, rather than doing an infusion of some other molecule. That's why this was used. Does everybody understand the difference between cardiac output and effective cardiac output, and why you would want to know the difference between the two if there is one? You shouldn't have one. If you're completely healthy and everything's working normally, they should come up with the same number. If they don't, there's a reason for that. Some of that blood is not going into circulation. Some of it is getting regurgitated back up. That is the end of cardiovascular. That was the last slide that I had. So we have about 5 minutes left. Does anybody have any questions? Yeah. So you could use this equally to test for congestive heart failure, but typically one of the things that you're going to notice is that somebody with congestive heart failure is going to have other symptoms, shortness of breath, they're going to have swelling depending on which side of the heart is affected. So usually those kind of symptoms will precipitate this effect, but you can figure out exactly how much their cardiac output is affected by this. Yeah. Guys, be a little quiet. They're still asking questions. If you want to pack up and go, I'm okay with that, but just keep it down, okay?
There's mixing from the wrong capillary bed, which is deoxygenated blood and the pulmonary vein. Why can you still measure any systemic artery and carry out gas?
Because what you're really measuring is you want to measure the value that's coming out. That is the, when you're doing the Fick principle, what you're actually measuring is the tissue usage. The way this is set up, what you really want to look at is you're measuring here and the amount that is leaving. It's the same setup as you would have up here, but you're taking, in this case, you are removing something from. So you're going from 20 down to 15. technically this would be adding it in, so you would have to come up with this difference here as well. The addition of that mixed venous return doesn't have a huge impact on the overall mils of oxygen per deciliter blood. It's so minor that it's not going to have as big of an impact on being able to measure from any systemic arteries versus from the pulmonary vein. But when you're doing this system, what you're really calculating is typically on the systemic side. You're measuring what is the arterial oxygenated blood going into the tissues, and then how much is being used by the tissues. It's just easier to measure the oxygen that's being produced and understanding that they should be